Hey everyone, welcome to Math 142. I'm Cole Easton. I'm the course coordinator and one of the instructors. For the summer, I am teaching section 142.01, and the other instructor is Shengzhe Duan, teaching section 142.02. Both of our sections are following the same schedule. We have the same exams at the same times. We have the same blackboard. But students are assigned a specific instructor, and you can see who you're assigned in UR Student. And you should check that again now, because when people signed up, everyone signed up under me, but then they shifted some students to be his students. So you do want to check to see who your assigned instructor is so that you can attend the correct synchronous lecture if you're able to do so. Some students, because of time zones or possibly other reasons, are unable to attend synchronous lectures, in which case you should be watching the asynchronous lectures like this video. And if that is the case, you're welcome to watch the asynchronous videos produced by either instructor. Okay, so the syllabus is something that you should have access to, and you should review the syllabus. You should make sure you understand, basically course expectations, exam dates, everything like that. I'm not going to spend time going through that right now, but certainly let me know if you have any questions about what it says on the syllabus. So today we are going to start out by doing a review of some of the most important things that are going to just keep coming up again and again. So that's concepts related to graphing, trig functions, and we're especially going to focus on graphing polynomials and rational functions, especially in the second half of the lecture today. If you feel like you're already pretty good at, and not just pretty good, but actually like very confident evaluating trig functions, and you can graph like the basic parent functions as we call them, and you know how to transform functions and everything like that, then you should be okay to kind of jump forward to the part of the video where I start talking about graphing polynomials, which sort of segues into rational functions, right? Polynomials are a special case of rational functions. And I'm going to put the timestamp for that on the screen here, so that you can just jump ahead and do that. And otherwise, if you feel like it might be helpful to review, then certainly I recommend just following along and watching the whole video. If there's certain parts that are seeming super familiar, of course you can maybe speed up the video 2x speed, try to get through those parts. And it'll just be these first 2 days where some parts might feel like review, but once we get to lecture 2, which is going to be on the third day on optimization, from there on out everything is going to be new material. All right, so let's get started. So today we're mostly going to be focused on reviewing some of the stuff that we did in 140 and 141. I know that some of you may not have taken 140 here. That course is called Foundations of Calculus. It's essentially the same as pre-calculus, if that's something that you've taken in high school. So especially for you guys for whom it's been a little bit longer, we just want to make sure that we've got all this stuff really comfortable so that we can work with it in this course. So the first thing we're going to look at is curve sketching. So hold on, let me just get my pen working here. Here we go. So we're just going to look at linear functions first. So let's say I had a function like y equals 2/3 x plus 1. So we want to remember that this is rise over run, right? So we think of this as being the rise, and this as being the run of the function, which means that, well, actually, let's just label this too really quick. So this is the y-intercept. The y-intercept. So the y-intercept means that this is our y-axis here, right? And this is our x-axis. So y equals 1. I'm assuming that the grid lines that I have on the background are actually the grid lines of this function, right? So 1, 2, 3. Y equals 1 is where we're going to intersect the y-axis. And then it means, so run is 3. So run means that we go over 3, and rise 2 means we go up 2. So we're going to kind of think about, we go over 3. I'm going to draw this dotted because this isn't actually the graph. Over 3 and up 2. And here we are. And so our line is going to be the line that goes right through these points, right? And so if we think about what this means, it means that like we could go back 3 and down 2 to get another point if we wanted. And then once we get all those, we can try to connect these with a straight line. Of course, if you had a ruler, it would make that a little bit easier. Right, and so that's the general idea here. We'll just do a couple more examples really quick, but I think hopefully most of you guys are already fairly comfortable with this. So if we had y equals 2x minus 2, we want to remember that 2, we can think of that as being 2 divided by 1. So we get a y-intercept of -2. And then our slope of 2 means that we go over 1 and up 2. So this is our next point. We go over 1 and up 2. Over 1 up 2, and we can do the same in the negative direction as well. So we could go back down here to get kind of a bunch of points just to help us kind of guide our line here. And this is a little bit hard to do with my pen, but just imagine that that's perfectly straight. So the next example we want to look at is y equals -2/3 x plus 1. And so we just want to make sure you're not getting confused by this negative. Remember that -2/3, one way we could think about that is -2 divided by 3, or we could think about that as 2 divided by -3, right? That's all the same. So we know we have a y-intercept of 1, so I'm going to start with a point right here. And then if I think about it this first way, it means that we have a run of 3 and a rise of -2. So we go over 1, 2, 3, and then we go down 2, right? Rise of -2 means down 2 instead of up 2. So that means I'm going to put my point here. So I could think about that way, and then draw a line through those 2 points and all the other points on that line. Or we could think about it the second way, where we have a run of -3. So that means I'm going to go back 3 at a rise of 2 up here, and then I'd put a point here. But we see either way we do it, we get this same line, right? The line that goes through these 2 points goes through that point up there, and vice versa. So we'll get this line here, and we could have done it either way. We only had to come up with one of those points to draw that, right? And of course, just to not neglect it, right? Our most famous linear function is our basic linear function, the identity function y equals x. And so that's just y-intercept of 0, right? That's important to point out, right? If I don't have plus something over here, it's basically plus 0. So our y-intercept is 0. We can think about that as being y equals x plus 0. So now we want to just look at some other types of functions that are going to be important. The first of those being power functions. So the most simple one that's not linear is y equals x squared. We can just kind of think about what happens when we plug inputs in. So our x-axis, our y-axis, so we plug 0 in. 0 squared is 0. We plug 1 in. 1 squared is 1. 2. 2 squared is 4. 3 squared is 9. That's not going to fit on this graph here. And then remember, when you square a negative times a negative is a positive. So we're going to get a positive out. And same thing over here. So we get this symmetry here. Now, if I did have a little bit more space, something that's important to notice is I go over 1 up 3. I'm sorry, I go over 1 up 1. I go over 1 up 3. Then I would go over 1 up 5, right? 9 is 5 more than 9. And then I would go over 1 up 7, because 16 is 7 more than 9. 16 is 4 squared. And I'm gonna keep repeating that pattern. So it's like it's 1, 3, 5, 7, 9, 11, and that's the amount that I'm increasing. And I'm counting up by 2, right? So if you did have a more complicated parabola, that's definitely a helpful trick to graph it, as long as your coefficient here is a 1. And I'll talk about that a little bit more later, but I just wanted to point it out right now with this simple example. Okay. And the other things we're going to look at are things like this, y equals x cubed. So, oh gosh, I'm gonna change my scale here. I'm gonna make this scale be 1, 2, -1, -2, just like it already is. And then this scale I'm gonna change a little bit. So I'm gonna go 2, 4, 6, 8. So each one of these is 2. So 1 squared, or 1 cubed, 1 times 1 times 1 is 1. So that's right here. 2 times 2 times 2 is 8. So that's up here. 0 cubed is 0. Now, negative 1 times negative 1 times negative 1, right? Negative 1 times negative 1 gives us positive 1, times another negative 1 gives us negative 1. So that's a negative 1. And same thing happens with negative 2. So negative 2 times negative 2 is positive 4. Times negative 2 gives us negative 8. So 2, 4, 6, 8. And that's going to be this point right here. And so let's try to sketch what this looks like. So that's going to look something like this. Okay. Now I also have a Desmos of some of these, just so we can get kind of a slightly better idea than my sketches. Okay, so x squared, we know this one. X cubed looks like this. And we're going to look at some higher powers too, because they may occasionally come up. So x to the fourth, it looks fairly similar in shape to x squared, right? The big difference here is that the bottom is a little bit flatter. And then x to the fifth, again, looks pretty similar to x cubed. It's just a little bit kind of flatter towards 0. And if we want to just specifically look at these even powers, right? So this is y equals x squared. You see it, the graph is labeled right there. It looks like this to the fourth, to the sixth, right? All these even powers, they have sort of the same shape. It's just that as we increase the power, it becomes flatter. And then if we look at odd powers instead, start with 3, 5, 7, 9. Again, all essentially the same, but they get a little bit flatter towards the origin. If I asked you to sketch these, even though the graphs look a little bit different, basically anything that's roughly this shape would be acceptable for any of these even or odd powers, because the differences are too subtle to be expected to graph. As long as you get, as long as your odd power looks like this and your even power looks essentially like a parabola. Of course, the one odd power that doesn't look like that is the linear function. That's not going to have that flatness at all near 0. So you shouldn't be graphing the linear function like a cubic or vice versa. Let's come back here and we're going to look at a couple other functions that are important to know how to graph as well. The next function we want to look at, well, in general, are exponential functions. And those are functions of the form b to the x. And that's contrasted with power functions, which are functions of the form x to the p, right? So what makes something exponential is that the variable of your function is in the exponent rather than being in the base raised to an exponent, right? So x squared is not exponential, but 2 to the x is exponential. So let's graph right here. We're going to graph the function 2 to the x. So that means 2 times itself, x times. We say that 2 to the 0. So let's actually make a little table over here, actually. We'll say x and then 2 to the x. And we'll do let's start with -2 actually. -2, -1, 0, 1, and 2. Okay. So we know that 2 to the first power is 2. So that's kind of the easiest one. 2 squared is 4. Let's go one more. Cubed, 2 cubed, so 2 times 2 times 2 is 8. So I'll put an 8 here. 2 to the 0 is 1. So anything to the 0 power is 1 except 0. 0 to the 0 is not typically defined. We say that it's an indeterminate form. But any other number to the 0 is 1. And that should kind of make sense if you look at this pattern, right? As I go from 8 to 4, I'm dividing by 2. 4 to 2, I'm dividing by 2. And then 2 to 1, I'm dividing by 2. And so maybe that gives you some insight as well as to what 2 to the -1 should be, because maybe we should just divide by 2 again, and that would be exactly right. That's 1/2. And similarly, 2 to the -2 is 1 to the 4th. But just to give a little bit more of a concrete reason for that, if we have 2 to the -x, that's the same as 1 over 2 to the x. So 2 to the negative 2, for example, is the same as 1 divided by 2 squared. So that's 1 over 4. And that's exactly what we found, even just by kind of following this intuitive pattern that we were seeing. So let's go ahead and graph this. So at 0, we should have 1. Notice I've changed my y-axis scale again. So 1 gives me 2. 2 gives me 4. 3 will give me 8. And then as we move in this negative direction, negative 1, that is there. Negative 2 is quarter. And if we kind of think about what's going to happen, right, these are going to keep, we're going to keep cutting them in half. But so they're never going to quite reach 0, but they're going to get really close. And they can never become negative either, right? Because they're positive, and cutting them in half is going to keep them positive. So let's do our best to kind of connect these points. All right, good. Generally, an exponential function is going to look pretty similar to this, regardless of what the base is. Probably our most famous exponential function is e to the x, and e is about 2.7. So, anything to the 0, like we said, I'm assuming the same scale on this graph is going to be 1, which is going to be right here. And then to the 1 is going to be a little more than 2, and so on. So when you're graphing exponentials, we don't expect really a high level of detail, just that you have this general level of, or this general shape where you're approaching the x-axis as you move in the negative direction, and you're kind of exploding upward in the positive direction. The next type of function we want to look at are logarithms, and they are the inverse functions of exponentials, just like roots are the inverse function of power functions. We're going to graph this type of function. We're going to graph function log2 of x first. But just for a second, I want to kind of talk about what logarithms mean, because I think I see a lot of times people being a little bit kind of unsure of exactly what a logarithm is. So let's just write down some stuff. So if I just had log base 2 of 32, basically what that is saying is it's, right, a function is in some sense always asking a question, right? If I say, what is 2 to the third, I could say that in English, and saying what is 2 when I multiply by itself 3 times. Or if I say, this is maybe a better example, if I say, what is the cube root of 8? My question is, what number, when I multiply by itself 3 times, gives me 8, right? And the answer there would be 2. So log base 2 of 32, our question here is, what power of 2? What power of 2 gives me 32? Right, so well, what our question is 2 to what here gives me 32? And whatever this question mark should be, that's the answer here. And so we can just kind of do some trial and error here, and we would find that 2 to the 5th is 32. And so that means that our answer is 5, right? This is, what power do we need to raise 2 to get 32? The answer is 5. Okay. And so that should help us think about how to kind of make the table here for graphing the log function. So we're going to see how many inputs do we want. 1, 2, 4, 8. Okay. This is a little bit slanted, but that's okay. Okay, so we're going to have, this is going to be our x column, and this is going to be our log 2 of x. So x is a half, x is 1, 2, 4, and 8. Notice that I'm strategically picking the x's so that my output is going to work out nicely, right? I don't want to ask the question, what power do I raise 2 to get 6? Because it's going to be some irrational number. But okay, what power do I need to raise 2 to get a half? If you remember before, when we were doing our exponentials up here, we found that 2 to the negative 1 gave us a half. So the power I need to raise 2 to get a half is negative 1. to get 1, remember it's 0. Anything to the 0 power gives me 1. Raise 2 to the first power to get 2. 2 squared is 4, and 2 cubed is 8. So let's graph these. So negative, so 1/2 is going to give me -1, so that's a point here. 1 is going to give me 0. 2 is going to give me 1. 4 is going to give me 2. And 8 is going to, it's kind of overlapping my writing up here, is going to give me a point up here. And let's try to add one more point, actually. So let's put it right here, and I want that to be a quarter. And if we remember from above, we found that -2, we found that 2 to the -2 gives me a quarter. So if we kind of look at our graph, just halfway between 0 and 1/2, and this little tiny interval is a quarter, and then that means that our output is going to be -2. And let's just think, I'm not going to write this down because we're kind of running out of space, but if we added 1/8 to this, we'd find that the output should be -3. And that's only halfway to this 1/4. And so we're going to have another point down here, -3. And then at 1/16, halfway between that and the origin is going to be -4. And so we can see that we're going to approach, we're going to kind of shoot down really quick as we approach the x-axis from the right, or approach the y-axis, I'm sorry, from the right. So let's just try to connect these points based on what we just reasoned about there. And we're going to come down like this. And also, if x is negative, we say 2 to what power gives me some negative number. It's not possible, right? We just looked at this exponential function, and we saw that 2 to any power is positive. So there's no way to get a negative number, which means that graphing this function to the left of the y-axis doesn't make sense. So this function is only graphed to the right of the y-axis, and it looks like this. And it is exactly the exponential function that we drew above, reflected about the line y equals x. So these are mirror images because they're inverse functions. Let's actually open up Desmos again, and we're just going to look at some of the functions we just talked about, just so you can get a really clear picture. Desmos is better at graphing than any human, so I think it's good to just get a sense of these graphs exactly as they should be drawn. Right, so our red graph here is the 2 to the x graph that we drew. We see that as we approach -infinity, it approaches this x-axis, and the log 2 of x, we have the same asymptote on the y-axis that we talked about. And if I draw the line y equals x, we can see how that line sort of acts as a mirror between these two graphs here. And I'm also going to draw or graph some other exponential functions. So I'm going to put e to the x here. That's this purple graph here. And we can see how that looks pretty similar in overall shape to 2 to the x. So if you're just sketching them, basically any given sketch that works for one should work for the other, as long as there's not a ton of detail. And the inverse function of e to the x is ln of x. So let me just hide these graphs with 2 really quick. So you can just see these graphs. And once again, they're mirror images of each other. And ln of x is exactly the same. It means the same thing as log base e of x, right? You see these are exactly the same graph because they mean the same thing. And so that's saying, what power do I need to raise e to get my particular x? Right. So I'm just going to do a quick example here in Desmos just to help you kind of wrap your head around this a little bit, because I think some people find this a little bit more abstract. So let's just take ln of 5, for example. So that's 1.6094. So what does that mean? That means that if I raise e to the power of, let me just type in that actual number, 1.6094. Of course, it's infinite, but you see how that equals 4.99909, right? So as I increase my accuracy, that's going to actually end up being 5. So e to that power that I got out is 5. And so that's what ln is telling us. One more thing that I wanted to look at in Desmos is functions of the form 1 over x to the n. So starting just by looking at this graph here, 1 over x, we see that it looks like this. So we have this asymptote at the y-axis. So, and we want to notice that as we approach the y-axis from the negative direction, we're approaching negative infinity. And that should make sense, right? We're plugging in some really small negative numbers, small in absolute value. So say 1 divided by negative 0.1. So that's going to give you negative 10, right? Negative 0.1 times negative 10 gives you 1. And kind of the opposite thing is happening in the positive direction. But now if we square this x in the bottom, right, then we have a positive divided by a positive because x squared is always going to be positive. So let's look at that. 1 divided by x squared, right? And so now this is always positive and we're approaching positive infinity from either direction. Let's go and try x cubed. What do you think it's going to look like? Looks sort of similar to 1 over x, right? This is 1 over x cubed. And this is 1 over x. Actually, let me just graph them both so you can compare. So you see the 1 over x cubed graph here. It essentially approaches infinity near 0 more quickly, right? Because if we think about what is 1 divided by 0.1 cubed, that's going to be 1 divided by 0.001. So whereas this one would give you 10, this one would give you 1,000, right? So as we approach 0, 1 over x cubed is approaching infinity faster, but sort of the behavior and the asymptotes are the same. And since the evenness or oddness is going to be the same, the sign of the function is going to be the same for any odd power, then if I change this to, for example, 1 over x to the 5th, 1 over x to the 7th, we're going to get the same sort of behavior. And so same thing with these even powers. So 1 over x squared looks like this. 1 over x to the 4th looks like this. Oops, that's 24th. X to the 4th looks like this, 6th, 8th, right? And so they all are more or less pretty similar. And in terms of a sketch, you really just have to pay attention to, is that power even or odd? And that's going to give you kind of the key features that you need to know in order to produce a reasonable sketch of these sorts of graphs. Okay. And just for kind of note-taking purposes, let's say 1 over x, and I'm just going to kind of quickly graph what sort of an acceptable graph of this would look like. I'm not even labeling the axes here. I'm just kind of graphing the shape. And oftentimes this is all you'll really need to do. Especially in this class, a question isn't going to ask you specifically to just graph a function. Usually you're graphing a function for some other purpose. In particular, when we get to the unit on areas, you're going to need to be you're going to need to know how to graph functions and find the graph at least the rough intersections of functions so that you're able to compute the areas between functions correctly. So this is 1 over x to some even power is also more or less always going to look like this. And 1 over x to any odd power, right? Notice this is really 1 over x to the 1, which is odd. And so 1 over x to any odd power is going to look more or less like this. Okay, the next thing we want to look at is trig functions. So let me just put a new axis here. Let's do a couple of these. Okay, trig functions. There is a few of them that we have to know how to do. So sine of x. Sine of 0 is 0. Let's put in our key points here. We know that sine has a period of 2 pi, which means that every 2 pi, it's going to repeat. So let's go 2 pi here. Pi over, well, that's 3 pi over 2. And this is pi over 2. Oops. Erase pi over 2. Okay. So sine of 0 is 0. Sine of pi over 2. Well, let's actually just graph a really rough unit circle here, just so we can kind of reason about what we're saying. So pi over 2 is this angle, straight up angle, and sine is saying what is the y coordinate of this. So that's going to give us 1. Just label these axes 1, -1. When we get to pi, that's saying that we've come all the way around here. And again, sine, maybe I should have mentioned this before, but sine is the y coordinate on the unit circle, and then we think of cosine as being the x coordinate on the unit circle at that particular angle. So when we get to pi, our y is 0. 3 pi over 2, we're down here at the bottom. So our y coordinate, that's the point is 0, -1. So my point's going to be here. And then 2 pi, we're right back at the beginning, and our y coordinate is 0. So let's try to kind of graph what this looks like. Smooth wave function, and that's going to kind of continue doing that same sort of oscillation. Oops. Okay. All right, now let's look at cosine of x. We're going to label the graph the same way. We're going to go pi over 2 pi, 3 pi over 2, and 2 pi. Now, okay, so we're starting at 0, so we're starting right here, and we're looking for the x coordinate. So the x coordinate of that is 1. And then when we get up to the top here, the x coordinate is 0, so we're at 0. Then we get over here, x coordinate is -1. 3 pi over 2, we're back at the bottom. X coordinate is 0. And then we make it back around to the initial point where our x coordinate was 1. So let's graph this. And notice that it is curved like this. It almost looks like because I graphed so few points, it almost looks like it should be a V, right? But that's not the case. It's the function's gonna look like this. Okay, we need to do at least a couple more trig functions that are going to be coming up a lot. We'll do tangent, secant, and arctangent. So let's look at tangent of x. Let's count by pi over 4s on this scale, and I'll add a couple in this direction. So remember that tangent is defined as sine of x divided by cosine of x. At 0, we know sine of 0 is 0, so this is 0 divided by 1, so that's 0. Let's draw another unit circle really quick. Pi over 4 is this angle, and we notice here that this is a isosceles triangle, right? The coordinates of this point on the unit circle at the angle of pi over 4 are √2 over 2, comma √2 over 2. So this is sine, cosine. They're the same number, so we divide them, we're going to get 1. So this is 1 right here. Okay, pi over 2, that means that we're up here at the top. So sine of that is going to be 1, right? That's the y component. And the x component is 0. So 1 divided by 0. So that's not defined. But let's think about what happens just a little bit before that, a little bit. So let's say like here, our sine is almost 1, and our cosine is almost 0, but it's positive, right? So we have a number, it's almost 1 divided by a really tiny positive number, and that means that we're like really big number. So pi over 2, as we approach that, we're going to approach a really big number. So let's kind of sketch what that's going to look like. And it's not even defined here, but we're going to get bigger and bigger as we approach it. And then off in the next, in the negative direction, we're going to kind of graph that too. So think about negative pi over 4. That's this triangle, which has the components √2 over 2, comma, negative √2 over 2. And so, right, I divide this by this, and I'm just going to be left with -1. And then kind of the same thing happens as I approach negative pi over 2, which is right here, our x is staying positive. It's getting really small. And our y is somewhere here. Our y is almost -1. So it's negative number, almost -1, divided by a really small positive number. That's going to be really big negative number. So we're like almost negative infinity as we approach pi over 2. So as we get closer to here, we're going to go down, 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 down. And so we have asymptotes here at pi over 2 and at negative pi over 2. And then after that, we're going to have this cycle just repeating again. So it's going to look like, oops, we're graphing lines here. We're going to have an asymptote here. Maybe -1 here, 0 here, 1 here, and another asymptote over here. And let's graph this on Desmos, because Desmos is going to do a way better job. Right, and so we see these asymptotes that we just kind of figured out a second ago, and then we have we see that we repeat over periods of length pi, right? So every pi, which is the distance between pi over 2 and negative pi over 2, we have that same kind of shape repeating. Just like we kind of talked about a second ago with logarithms, sometimes it's helpful to think about inverses in terms of a question. So arctan of x is the question, tan of what gives me x? So if I said arctan of 1, so that's saying tan of something equals 1. And so what's that something going to be? Well, it seems like maybe there's a lot of answers, right? Because I could plug in pi over 4. I could plug in, so this over here is going to be 5 pi over 4, right? So those are both work. But the problem is that arctan, we need it to be a function, right? And remember that a function has only one output for any input. So we're going to say that our question mark here is going to be pi over 4. And so we're always going to pick an answer that's between negative pi over 2 and pi over 2. Even though there's an infinite number of answers, since it's just going to keep repeating. So we're going to pick the answer that's in this range. And there will always be an answer, right? Because every output occurs. I could say, well, what gives me 10,000? Well, since this approaches infinity, somewhere in here is going to give me 10,000 as an output, and I can figure out the input that gives me that. So arctan of 1 is pi over 4. So arctan of 0, right? Tan of what gives me 0? That's 0. I'm going to make this look like this. Pi over 4, pi over 2. That's going to be my y scale. So 1 gives me pi over 4. And if we think about what happens here, notice that if I plug in a really, really big number, that say I plug in like 10,000, the output is going to be pretty close to pi over 2, right? So it's going to be somewhere like this input, right, is going to give me really big number. So as our input here goes really big, we say, what do I need to take tan of in order to get that number? It's going to approach pi over 2. So our limit here is going to look like this. It's going to be an asymptote approaching pi over 2. And the same thing in the negative direction. If we plug in, we say, what do I need to plug in to get a really big negative number? Well, as we approach negative pi over 2, we can get any really big negative number. So we're going to go like this, and then we're going to approach negative pi over 2 in this direction like this. And we have this point here too, right? We plug in 1, -1 gives us negative pi over 4. Because what do I need to plug in to get -1? It's right here, it's negative pi over 4. And let's look at that in Desmos really quick too. Arc tan of x looks like that. I want to keep the tangent on the screen for 1 second, just so you can notice how the arctangent is the tangent reflected over the line y equals x, because it's an inverse function. except we're only using the one piece of the tangent function. Because if we used all of them, it wouldn't be a function anymore. So we just have to select a piece and reselect this piece that goes through the origin as the piece to flip. And then we end up with this function here as arctan of x. So the big things to remember about this function is it has these asymptotes, y equals pi over 2 and y equals negative pi over 2. Because sometimes we're going to be talking about limits of this function. And so the really important fact to remember is that the limit, I'm going to actually write this down in here, is that the limit as x approaches infinity of arctangent of x is pi over 2. And the limit as x approaches negative infinity of arctangent of x equals negative pi over 2. Okay, so those are our important facts. And then we do just want to remember that it kind of goes through the origin like this and have a general idea of how to sketch that. Couple other things to point out about this function is that arctangent of x is the same thing. People sometimes like to write it like this, as tan inverse of x. But that is not the same thing as 1 divided by tangent of x. And that can be a little bit confusing, right? Because sine squared of x means sine of x squared. So you might think that tangent to the negative 1 of x means tangent of x to the negative 1, right? And the fact that it doesn't equal that, it's just basically an inconsistency in mathematical notation. I think probably we shouldn't use that notation, but people do, so we just have to kind of accept it and recognize that it doesn't really make perfect sense. But tan inverse of x is arctan of x, not 1 over tan x. But by the way, what is 1 over tan x? Because you do actually, this is something that may come up. 1 over tan x is cotangent of x, which is not the same as arctangent of x. Cotangent of x, 1 over tan x, arctan of x is the inverse function of tan x. Okay, cotangent of x is the multiplicative inverse of tan x. Different things. Okay, what is next? I think while we're on the topic, we should just briefly talk about a couple other inverse trig functions. I'm not going to graph them, but I think they're relevant to talk about at least briefly. So sine inverse of let's just do some examples really quick so I can we can reason about these. So what if I said what is sine inverse of root 3 over 2? So that is saying sine of what is root 3 over 2? Well, let's kind of think about our unit circle here. And ooh, this is a little bit messy. If we have an angle here of let's zoom in a little bit on this. If we have an angle here of pi over 3, then this point here is going to be the x coordinate is 1/2 and the y coordinate is root 3 over 2. And so the answer to this is going to be pi over 3. And similarly, cosine inverse of cosine inverse of 1/2 is pi over 3, right? Because this is the angle that gives us an x value here of 1/2. Right? Or in other words, this is the same as saying that cosine of pi over 3 is 1/2, right? Just by virtue of this question that it's asking, it's essentially the same as switching the inputs and outputs, right? And let's just do one more I'm going to use the same input that I used in the sine. So what's cosine inverse of root 3 over 2? So that's saying cosine of what gives me root 3 over 2. And so we'll draw another unit circle, and we're thinking that we want, let's draw this real quick. We want the x value to be root 3 over 2, so it's somewhere here. And this angle right here is going to be, gives us root 3 over 2. It's going to be pi over 3. I do think the unit circle can look a little bit scarier than it is. So really quick here too, I'm just going to talk about kind of a simple trick to think about the unit circle that's a lot simpler than a lot of people make it out to be. So we can basically divide a circle here in two ways. So the first way is we can think about it as being divided into quarters, like this. And I'm just going to remember one single point. Just one thing I need to remember is that this point is root 2 over 2, comma, root 2 over 2. And right, this is a unit circle, so I don't even think I should need to write this point or this point. But right, this is the x value is 1, the y value is 0, and the x value is 0, y value is 1. And you can do the same thing over here, right? This is -1, 0. This is 0, -1, right? Okay. So now what if I said something like, what is cosine of, let's see, of 5 pi over 4? So I'm saying, okay, so this right here is pi over 4. This is pi over 4. And we want 5 pi over 4. So we're going to count 5 of these. We're going to go 1, 2, 3, 4, 5. Okay, so I'm right here. And that means that I want these coordinates. And now all I have to do is just try to translate the signs, meaning plus or minus of these. So since this is to the left of the y-axis, we have negative root 2 over 2, and it's below the x-axis, so it's comma root 2, negative root 2 over 2, right? So negative, negative, and cosine, right, means x coordinate. So that's going to be negative root 2 over 2. If I said, what's cosine of 7 pi over 4? I would go 1, 2, 3, 4, 5, 6, 7. So that's here. I'm going to do this. Now the x coordinate is positive, so it's root 2 over 2, negative root 2 over 2. And so I'm going to take, again, the x coordinate, so that's root 2 over 2. Okay. And same thing with sine. So if I said, what is sine of 5 pi over 4? I'm going to grab the y value of this thing that I found here. And so that's negative root 2 over 2, or sine of 7 pi over 4, grabbing the y value of that second one. Well, that's also negative root 2 over 2. But if I just did sine of pi over 4, that's root 2 over 2. But you see, I have all of these different options, and I can figure out the outputs very easily, right? I don't really have to do much thinking. If I had something over 2, right? So if I had sine of, what's sine of 3 pi over 2? Well, I can think about that as being sine of 6 pi over 4, just multiplying the top and bottom by 4. And I can use this once again. So 1, 2, 3, 4, 5, 6. That gives me this. And that's just right on the y-axis. So x is 0, y is -1. And so sine of that is the y coordinate, which is -1. Okay. So we can figure out all of those with just basically that one single coordinate point that we have to think about. And there's only one other single coordinate point that we have to think about when we're working with a unit circle. And so we'll do that now. So besides the picture that we just looked at, where we divided the top semicircle into quarters, or each quadrant in half, what the picture that I've drawn here is really the only other thing that you need to have memorized in order to use the unit circle. So in this picture, we divide each quadrant into thirds. And what you need to memorize is that the terminal point of this first third, this pi over 6 angle, is root 3 over 2, comma 1/2. Now, the way that I like to think of that angle is as a triangle sitting on the x-axis like this. If we think about what these coordinates mean in terms of this triangle, since the x-coordinate is root 3 over 2, it means that this bottom side of our triangle has a length of root 3 over 2. Hold on one second, my pen is losing connection. Root 3 over 2. The height here is 1/2. And that is not a 3, that is a brace. So we can draw this triangle anywhere and essentially use these known values. We know that the short side is 1/2 and the long side is root 3 over 2 for any of these thirds, because it's symmetric all throughout. So let's do an example and let's try to find cosine of 11 pi over 6. Okay. So these thirds of quarters, right, are sixths of our upper circle, which has an angle of pi. So each one of those is pi over 6. So we're going to count 11 of those. So let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. That turned into a circle, but we found out that we wanted this angle right here. Let's see if I can erase that circle. Okay. We got that angle right there. And so let's try to draw a similar kind of triangle picture. Let's draw our axes. And now we have a triangle that's right here. And so this is our short side right here. That is length 1/2. Here's our long side, root 3 over 2. We're looking for the coordinate, basically, right here. We're root 3 over 2 to the right of the y-axis, so the x-coordinate is root 3 over 2. And then since this short side has length 1/2, but it's going down from the x-axis, that means that the y-coordinate is negative 1/2, right? Because we're in negative y. So if we go back up here to our cosine of 11 pi over 6, cosine is asking for the x-coordinate, so that is root 3 over 2. And then let's go and just answer the other question that kind of immediately follows, which is what is sine of 11 pi over 6? And since we already found the angle, we already drew our triangle, we know right away that that is negative 1/2. Okay. Let's do one more. Let's try cosine of, let's actually do this. Let's do cosine of negative 2 pi over 3. And we want to turn that into sixths. So that's cosine of negative 4 pi over 6. I'm multiplying the top and bottom by 2 there. So instead of going our normal counterclockwise direction, right, which is the positive direction for angles, we're going to count clockwise here. So we're going to go 4. We're going to go 1, 2, 3, 4. And so this right here is our angle. And we're going to draw a little picture of our triangle. So our triangle looks like this. And now the short side is right here. That's the 1/2. The long side is right here. So that's a root 3 over 2. And then let's think about what's going on with this coordinate. So the x, we are 1/2 to the left of the y-axis. So the x is negative 1/2. And then we're down root 3 over 2. So that's going to be negative root 3 over 2. So that means that our cosine, which is our x coordinate, is negative 1/2. And if we wanted to do sine, sine of negative root, or negative 2 pi over 3. That's going to be the y value, which is negative root 3 over 2. Okay, so that was a little excursion, but we want to get back to, well, to graphing functions. So one more trig function that we do want to think about, it's going to come up a lot, is secant of x. So let's graph this. And secant of x is 1 divided by cosine of x. Maybe we'll make a table for this. That might be kind of helpful. I think we don't look at secant as often as cosine, so we might not have as good of an idea. So let's think about what we normally plug into cosine. So we plug in, so this is going to be our x, this is going to be we'll actually do 3 columns. We'll do x, we'll do cosine of x, and then we'll do one more here for secant of x. So we'll go 0, pi over 2, pi, this will be 3 pi over 2, and this will be 2 pi. Okay, so cosine of 0 is 1. So that means secant 1 divided by 1 is 1. Cosine of pi over 2, well, that gives us 0. So we'll think about that in a second. Cosine of pi gives us negative 1. This gives, okay, 1 over negative 1 is negative 1. That's fine. But then we get another 0 here. And then 2 pi gives us 1. So we're back to 1 again. Okay, so let's see what we can do here. So we know that we get a point here at 1, 1. Or at, what am I saying? Yeah, at 0, 1. Let's kind of graph, or let's label our axes really quick. Pi, 2 pi, okay. So we know we have this point. At pi, we have negative 1. And then at 2 pi, we have 1. So the issue is that we know that as we approach pi over 2, we sort of have this issue of this is undefined, and this is also undefined. But if we think about what happens with cosine, as we, let's really quickly just kind of draw cosine here. Cosine looks like this, right? This is pi over 2. So as we approach pi over 2, we have a positive number that's getting really small, and we divide by 1 divided by a small positive number is getting really big. So that means that as we approach pi over 2, we should be getting bigger and bigger and bigger from this side. But then on this side, as we approach pi over 2, we're approaching 0, but we're a negative number. So we're a really small negative number. So cosine of, say, pi over 2 plus 0, 0, or 0.001 is going to give us a really small negative number. We divide by that, we get a really big negative number. So we're going to approach negative infinity from this side. And the same thing happens over here, right? We're approaching, as we approach 3 pi over 2, cosine approaches 0 on the negative side. And so we're approaching negative infinity. But then we can think about, again, over here, we're approaching 0 from the positive side. So really small positive number, divide by that, get a really big negative number. And so we end up with a function that looks like this, and it continues along like this. We could kind of keep repeating this argument. We'd keep saying the same thing. And so let's just look at Desmos' version of that really quick too. Secant of x, right? And it looks just like this. If we compare that to cosine of x, we see that the places where cosine is 0, right? Where cosine is 0, that's where we get these asymptotes. And right as we approach 0 from the positive side here, we get these big positive numbers. And as we approach 0 from the negative side, that's where we get these big negative numbers. So it approaches negative infinity. Now we're going to move on to our next main topic, which is graph transformations. So Let's start with a function that we know how to graph. I'm going to use the function sine of x, because I think this is good at illustrating a lot of these transformations. So, okay. So now let's just graph sine of x really quick. Sine of x, what are our important values? We're going to go pi over 2, pi, 3 pi over 2, and 2 pi. We start at 0. We're going to go up to 1 here, back down to 0 here, over to -1 here, and back up to 0 here. Okay, great. And this is sine of x. Now let's do new graph. I'm going to relabel the axes the same. By the way, this is 1. This is -1. Pi over 2 pi. And this time I want to graph sine of x plus 1. So what does that mean? So we think about with this graph, we take some number, we take some x value, and then we take the sine of it, and that's the y value. So here we're going to take some number x, we're going to take the sine of it, and then we're going to add 1. So 0, we take the sine of it, we get 0, and then we add 1. Pi over 2, we take the sine of it, we get 1, and then we add 1, and now we're up to 2. Pi, sine of pi is 0, plus 1 gives us 1. Sine of 3 pi over 2 gives us -1, plus 1 gives us 0. And then we plug 2 pi, sine of 2 pi is 0, plus 1 is 1. So our new transformed graph looks like this, right? And it should make sense, right? Since we're adding 1, we're basically pushing all the points of the graph up by 1 unit. So when you're adding this 1 kind of outside of the function like this, you're shifting the function up, right? And similarly, if I subtracted 1, I would be shifting the function down. So let's look at this example in Desmos just to kind of really nail it down. So sine of x plus c, so this is sine of x plus 1, like we had before, c is 1. And as I add higher numbers, it's going to move up. And if I subtract numbers, right, so this is our original function, c is 0. If I say sine of x minus 1, for example, it's going to look like this. Right, and anything we do, it's just moving the function up and down like this. Good? Okay, let's go back to OneNote and let's look at something a little different. Let's go sine of x. And inside of here, I'm going to say it's sine of x minus pi over 2. And before I graph that, let's just extend this graph a tiny bit. Because what happens when I plug negative pi over 2 into sine? That's going to give me -1, right? But we don't want an arrow. How do I delete this? Okay. Okay. It's going to give us -1. So sine of x minus pi over 2, let's start by plugging in 0. So we plug in 0 for x, and then we subtract pi over 2 from that. So then we're taking sine of negative pi over 2, and we said that that was a -1. Okay. Now we plug in, let's not get ahead of ourselves. Let's label the axis here, 3 pi over 2, 2 pi, 1, -1. Okay, so we have this. We plug in pi over 2 for x, and then we end up with sine of 0. Sine of 0 we said is 0. Now we're plugging in pi, so it's sine of pi minus pi over 2. That's sine of pi over 2, which is 1. 3 pi over 2. So now we have sine of 3 pi over 2 minus pi over 2. That's sine of 2 pi over 2, which is sine of pi, which is 0. And now we're going to plug in 2 pi over 2. So, sorry, plugging in 2 pi, so it's sine of 2 pi minus pi over 2. That gives us sine of 3 pi over 2, which is -1. So we'll connect these and draw our graph here. And let's just kind of think for a second about what happened here. So when I plugged 0 into my function here, what I really got was what I should have gotten when I plugged negative pi over 2 into my function here. And same thing, I plug in pi over 2, and I got what I would have gotten from 0. So in some sense, it's like I'm taking my original function and I'm just moving it pi over 2 to the right. All right. Is that making sense? Because I'm taking these points and I'm subtracting pi over 2. And so the reference point in my original function is pi over 2 to the left. So I'm shifting the original function pi over 2 to the right. And you can see that here, right? Because this 0 moved from the origin over to here, which is a shift to the right of pi over 2. And let's similarly look at this on Desmos. So if instead we have sine of x plus c here, it's kind of start at 0. So this is our original function. And when we subtract a little bit, you see where c becomes negative, our function moves to the right. And as c becomes positive, our function moves to the left, right? So we're kind of moving in some sense the opposite direction that you would expect if you don't think about it hard enough, right? But if you really think about it, it does make sense that positive is moving to the left and negative is moving to the right. Okay, let's do another one. Let's do 2 times sine of x. Okay, so sine of 0 is 0, times 2 is still 0. Sine of pi over 2 is 1, times 2 is 2. Sine of pi is 0, times 2 is 0. Sine of 3 pi over 2 is negative 1, times 2 is negative 2. Sine of 2 pi is 0, times 2 is 0. Okay, so what happened? Every output to the function we multiplied by 2, right? So our function got really, it got a little bit taller. So let's look at just kind of a generalization of that in Desmos. So we have, well, our original function is c is 1 right here. We made c 2, and so it's stretched up like this, right? The bigger we make c, the more we're kind of stretching it up and down, right? And if we were to make c negative, then we're flipping it over the x-axis. Okay, so we might look at that case specifically in a moment too, of making things negative. So let's do something else though. Let's go sine of 2x. Right. And I just want to point out too, right? And we kind of saw this at Desmos, that if instead of a 2 here, we had like a 1/2, then instead of getting taller, it would get shorter, right? Okay, so sine of 2x, let's graph this. I'm gonna, well, yeah, I want to keep the axis the same so we can compare it. So we're gonna go pi over 2 pi over 2 pi. Except I want to think about some points in here as well. So I'm going to think about pi over, well, first I'm going to think about 0. So sine of 0, sine of 2 times 0, sine of 0, that's 0. Sine of pi over 4 times, so x is pi over 4, right? Times 2 gives me sine of pi over 2, and then sine of pi over 2 is 1. So for x equals pi over 4, we're getting 1 out of that. When x is pi over 2, we're taking sine of 2 times x over 2, that's sine of pi, so that's 0. Now I'm going to look at this point right here. So this is sine of 3 pi over 4. So x is 3 pi over 4. 2 times 3 pi over 4 is 3 pi over 2. And sine of 3 pi over 2 is negative 1. So I'm going to plug my negative 1 down here. And then x is pi. So sine of 2 times pi, sine of 2 pi is 0. So we've constructed basically an entire cycle right here. And then because pi just repeats, we're going to have the same thing happen one more time before we get to 2 pi. So in this case, we basically squeeze the function horizontally. It's called horizontal compression. Right. What we did above is called vertical stretch, and I'll write that below. And this is called horizontal compression. But really, the intuitive idea of what's going on is much more important than these names. Ultimately, you're not being tested on the names. It's just important that you understand how to manipulate functions in this way. So we'll put a C in here. We'll start with this being 1, and then we made it 2, so it got squeezed in like this. And the higher we make it, right, we see the more we're squeezing it in. And if we make it less than 1, we're actually kind of pulling it out. And when we pull it out, we call that horizontal stretch, right? And similarly, like before, when we had that C out in front, if we made that C less than 1, that would become a vertical compression, right? Because it's getting less tall. And so maybe I should distinguish that. So we're calling, so this is our C value here. So vertical stretch is for C bigger than 1. And we call that vertical compression for C less than 1. So horizontal compression is for C bigger than 1, and horizontal stretch is for C less than 1. Again, this isn't really something that you need to memorize, because if you just kind of think about what's going on, you should be able to work it out. And these names and stuff aren't very important. Okay, so we have those. Let's see. If we wanted to graph a negative sine of x, we essentially saw this before. Actually, really what I mean here is this is the absolute value of C, right? When I say C less than 1, I'm not talking about -8. I'm talking about like 0.5. Okay, negative sine of x. So what's that going to look like? Pi over 2 pi, e pi over 2, 2 pi. Okay, so sine of 0 is 0, negative of that is still 0. Sine of pi over 2 is 1, negative of that is -1. Sine of pi is 0, negative of that is 0. Sine of 3 pi over 2 is -1, negative 1 is +1. And 2 pi gives us 0. So we get a graph that looks like this. All right, and so as should kind of make sense, right? We're just flipping this graph over top of the right over the x-axis, because every y value just becomes its own negative. Let's see, we need to use a little bit of a different function. Well, no, we don't really to do this. We can look at this like this. So we can do sine of -x. And I'm just going to graph this in a different range, though, because I think it gives us a better sense of what's going on. Negative pi, -3 pi over 2, negative 2 pi. So I'm kind of comparing this graph to the graph we drew before. So of course, 0, -0, 0. So if x is pi over 2, negative pi over 2, or negative pi over 2 gives me pi over 2. So sine of that is 1. Sine of pi is 0. Sine of 3 pi over 2, right, which is negative 3 pi over 2 is -1. And then we go like this, right? So the reason I'm picking these inputs is because once I apply this negative to these inputs, I get the inputs that I had before. And so you can kind of reason that what's going on here is the graph is reflecting about the x-axis, right? Of course, both of these graphs they extend infinitely. So both of these graphs look like this. And so they look identical in this particular case because it's the sine function. And I'm going to talk about that in 1 second too. So the reflection over x-axis is when we do it outside. When we do it inside, it's going to be reflection over y-axis. And I'm going to pick a better function to do this, to illustrate this as well in 1 second. Right. And so the reason that these are the same is because sine is what's called an odd function. Right. Odd functions are functions of the form. Odd functions is when f of negative x equals negative f of x. And even functions is when f of negative x equals f of x. Right? Some functions and probably most functions are neither of these, but sine is what we call an odd function, which essentially means that reflecting over either axis does the same thing. But let's look at a different example here. So let's go, actually, this is a good example because we're going to review the translation stuff one more time, and then we're going to use that to review the reflection stuff. Okay. So I'm gonna start with my function x squared. I'm gonna say f of x equals x squared, and I'm gonna say g of x is x minus 2 squared plus 3. Or no, that's just not going to fit on my graph. Let's do something a little different. Let's go x minus 1 squared plus 2. Okay. Okay, so let's think about what's happening. So if I shifted this 1 unit to the right, that's going to give me this part, right? This is f shifted 1 to the right. And this, overall, it's this shifted up 2. So, okay, so we know that f is kind of something like this. That didn't turn out right. Let's see. Okay, something like this. It's a parabola. We want to shift that 1 to the right and then up 2. So our new vertex is here. And if you remember quite a while ago, I was talking about when we draw parabolas, we can go over 1, up 1. And then now this is kind of way out of the range of my coordinate axis, but over 1, up 3. Over 1, up 3. And so this is especially helpful when I'm kind of not at my axis and I can't easily plug in like, 1, 2, 3. This just gives me a better sense of how to draw my parabola from wherever I am. And again, that only works when my a value of the parabola is 1, right? Since there's essentially a 1 in front of this x, that's what allows me to use that trick. Okay, so here's my function g of x that we used our translation rules to use, right? Both of these are called translations, right? This is And again, the names aren't important, which is why I didn't even mention it, but this is a vertical translation. Translation is basically a fancy word for movement. Um, and this is a horizontal translation. Okay. All right. So we used our translations to figure out G. And now let's apply some things to G. So let me draw a new axis here. Okay, and here let's graph negative G of X. So that means that we're taking G and we're reflecting it over the X-axis. So our new vertex is going to be right here, is going to be, because here it was 1, 2, it's going to be 1, negative 2. And then we're going to basically draw our parabola coming down this way. Okay. So that's this. And now let's do the other reflection, the horizontal reflection, which is so here we're going to graph G up negative X. So we're going to take this and we're going to reflect it over the y-axis, and that's going to be here. And then same thing, we'll just kind of graph. I don't want to overlap too much of that stuff up there, so we'll just kind of truncate that there. And that's my G of negative X. Okay, so that's basically what we need to know about graph transformations. Just a quick rundown. If you're feeling totally lost with this, might be a good idea to look up some more videos about this stuff, because it will come up a little bit, but this is kind of just the gist of what you're going to need to know. Now we're going to have a look at something in Desmos, because I think this is going to help us with the next thing we're going to do. So let's just start by looking at a function like this, a function x minus 3 cubed, and let's graph another function too. Let's do x minus 3 squared. Okay. Now I want us to think about what's going to happen if I multiply these two functions together. Okay. So let's look at this root right here, this 0 of x minus 3. And when we multiply it by this other function, right? This other function has the value of 9 at 0. So kind of right around here, we're just stretching the area around this root by a scalar of 9. So it's basically a vertical stretch of 9 around this root, which means that the overall shape of the root is staying the same. And if we look at this root here, well, x cubed of 3 is going to be 27, which means that we're kind of scaling the region around this root by a factor of 27, but still the shape of that root is going to stay the same, right? It's still going to be this quadratic root. And so let's just look at what we're saying here. So x cubed times x minus 3 squared, right? And so this is the product function, right? We see that around this root, we're really stretched up. We're stretched up actually by a factor, like I said, of about 27. And around here, we're stretched up by a factor of about 9. But I don't really care about those scalar factors. That's not something you need to really think about. You're not going to be asked about it. But the key idea here is that the shape of the roots aren't changing. So if you were just given this function, this black function here, factored in this way, what you would need to recognize is that there is a root at x equals 3, right, which you'd get by solving by setting that second factor equal to 0, and that root looks like a parabola, right? That the graph touches the axis there. And remember before that when we looked at all of our different power functions, we had all these power functions with even powers, and we saw that they all looked essentially the same. So if this was a 4, that still looks pretty similar, right? If this was a 6, right? Ultimately, like in terms of a sketch, your sketch would look effectively the same, regardless of what even power we had here. And same thing with this cube. If I made that a 5, still looks more or less the same. 7 looks more or less the same. But if it was a 1, this is an important difference here, is that if that was a 1, then we kind of think about that's like this original function being a line, and then we're scaling that line up. And when you scale a line, right, it looks significantly different because it's crossing transversely through that axis, as opposed to when we have a cube. Oops. When you have a cube and it sort of becomes briefly parallel to the axis. Okay. So let's go over to OneNote here, and so we're going to call this graphing polynomials. So you might need to factor a polynomial, or a polynomial might be given to you factored. Again, this is not pre-calculus, or this isn't really going to be the focus of the course. But it's just good to kind of understand how to do this, and this is going to be the focus of the first web work. So you do need to know how to do it. So let's say we have, let's say we're given something like this, x minus 1, x plus 2 squared. And let's do something like this. No, I want that to be squared. X squared plus 1. Okay, so we're given this polynomial, and we want to graph it. Okay, so first thing we want to do, there's really main things we want to look at are these things. End behavior. End behavior, roots, and multiplicities. Oops. Roots and multiplicities. Okay, let me just rewrite this word. Roots and multiplicities, and the y-intercept. Just knowing all these things will give you a very good idea of what a polynomial is going to look like. End behavior. So let's actually go back to Desmos. Desmos is a fantastic tool. Okay, graph of x looks like this. So as we approach positive infinity, right, as we walk to the right, our function rises. So people like to say it rises to the right, falls to the left. That's fine. I think it's pretty informative. If I had negative x, right, falls to the right, rises to the left. And same thing with x cubed, same thing with x to the 5th. In terms of end behavior, every odd power function is going to be the same. Okay. So, right, if it's even, I'm sorry, if it's positive, it's going to just look like the graph y equals x. It's going to have the same behavior as y equals x. If it's a negative, it's going to be like y equals negative x for any odd power function. And then if we have x squared, it rises to both sides, right? Rises to the right, rises to the left. Negative x squared falls to the left, falls to the right. So let's guess we can just do a quick little table of of behaviors just to kind of remember. So I guess ultimately there's 4 of them. So I'm going to go x to the odd, and I'm just going to draw arrows here. So it's right. So it falls to the left, rises to the right. We have negative x to an odd power, rises to the left, falls to the right, right? It looks like negative x, right? Because that is such a function. If we have x to the even, right, that's basically has behaviors that look like x squared. And if we have negative x to the even, what is going on? Then it's going to look like this. Right? It's going to fall to both sides, fall to the left, fall to the right. Right, just like negative x squared. Okay. So now this depends on the overall function when we multiply it out. And right now, most of the time, we're not going to have a simple function that's just x to some power. We're going to have something bigger, like negative x to the 5th plus 3x to the 4th minus 2x plus 7. Okay. But regardless of what other terms we have here, we're always going to just look at the leading term. So that's the term with the highest power, the degree of the polynomial. So this is a polynomial of degree 5. Our leading term is this right here, is negative x to the 5th. And so that's all we're going to look at. So this is going to have the same end behavior as negative x to the 5th, which says that it rises to the left, falls to the right. And just looking at this green function here, we can see that that's true, right? And this will always be true for any polynomial, regardless of what these smaller power terms are. The end behavior is the end behavior of the leading term, because it ultimately, as we approach infinity, becomes much bigger than all the other terms, and it completely overpowers them. So now I don't really want to FOIL this whole thing out. I don't want to expand this whole polynomial because that's going to be gross and it's going to be a lot of work. But I just have to think about what's going to happen when I multiply it out. So because I only care about one thing, that I only care about the highest power term, and that's going to happen when I multiply this x by, so when I expand this, I'm going to get an x squared, right? It's x times x. So it's going to be x squared times x squared. So it's going to give me x to the 5th, right? Maybe I should just quickly point out, if you didn't catch that, is that this term right here is going to be x squared plus, and actually I don't even care what the rest of it is, right? But it's because this is x plus 2 times x plus 2, right? So x times x gives me x squared. And so I have an x squared here. And then I'm multiplying this x times this x squared, this x squared times this x squared. And so that gives me x to the 5th. So that's my end behavior. It's going to look like x to the 5th, which is x to an odd function. So that looks like, or x to an odd power, so that looks like this. And so let's kind of start drawing what we have here. So I'm just going to kind of make a little mark like over here, saying like it rises to the right, it falls to the left. So kind of as I go over here, I'm getting up high. Oh, it made a hexagon. Let's erase that. Okay. Let me just erase these two. Okay, so that's the end behavior, which I just denote by these marks. Off to the right, it's up. Off to the left, it's down. The roots and multiplicities. So the roots are when our function equals 0. So we can set our factors equal to 0. So x minus 1 equals 0. It gives us x equals 1. So we have a root right here, and it has multiplicity 1, right? Which means that the power of that is 1. So there's a 1 right here. essentially. And so if we remember what we looked at before in Desmos, that means that the graph is just going to go transversely through that point. Okay, let's look at another one. So we have x plus 2 equals 0. And so x equals a -2. Okay, so that is right here. And this is a quadratic root, right? So this is going to look like a parabola on that root. And there's no more roots, right? If I say x squared plus 1 equals 0, then I get x squared equals -1, and there's no solution to that, right? I can't square a number and get a negative number. So that factor yields no roots. Okay, so I have this root, multiplicity 1, and this root here, multiplicity 2. So I'm gonna try to figure out one more thing before I graph this, and that is what is our y-intercept? And y-intercept means we just plug in x equals 0, right? Because that's the output of the function when x is 0. So I get -1 times 2 squared times 1. So that's -4. Okay. So my y-intercept is -4. So I'm going to put a point right here at -4. And that's all the information that I really need to get a pretty decent picture of this graph. So I'm gonna start at this kind of end behavior point, and I know that I have a root here, so I know I have to touch the axis here, and I know that it looks like a parabola at that point. So that means that I have to go back down here, and then I'm gonna have a y-intercept here, so I have to cross that, and then I have to go through the axis again here, and that is crossing it transversely like a line like this, and then I have to make it back over to this point here. So that's essentially what this graph is going to look like. And let's see how good we did. So we're going to go x minus 1, x plus 2 squared, and then the last one was x squared plus 1. Let's see. Okay, so not too bad. Not too bad, right? So we hit this point, we went through this point, we got those end behaviors right, we have this y-intercept. Kind of some of this weirdness we weren't going to be able to predict, but that's okay. Our sketch is fine for this graph. We captured kind of the key features that we wanted to. Maybe let's do kind of one more example like that. Let's just go, let's go negative x minus 1 cubed times x plus 2. Okay. Okay, so let's again kind of think about our end behavior. So first of all, this is going to be, when we FOIL this out, this is going to be kind of x cubed plus blah, 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 times x plus 2. And we have a negative here. So that's going to equal negative. I'm going to multiply these x's together eventually. Negative x to the 4th plus something. So our leading term is going to be negative x to the 4th, which is like this right here. So it's negative x to an even power, which means that we have kind of end behavior coming down here, and it's going to come down over here too. Okay. Our roots. So we have one root where x minus 1 equals 0. So that gives us x equals 1. And then we have x plus 2 equals 0. And so x equals -2. So we have a root right here. And we have a root at x equals 1. And we remember that the root here has multiplicity 1 for the -2 root. So we're going to transversely go through that. and the other one is cubic, so we have to kind of go flat on that root. Last thing is we want the y-intercept, so let's just go 0 minus 1, the negative out here, cubed 0 plus 2, so that's a negative 1 cubed times 2, negative 1 cubed, negative 1 times negative 1 gives us 1 times negative 1 gives us negative 1, so that's negative 1 2, which is 2. Those negatives are going to cancel. So we have a point right here at 2. Okay, so let's see. So we have to go up and approach our root here at negative 2. This is our linear root, so we're going to just go straight through it like this. And then this root is our cubic root, so it should kind of look like a cubic function on there. Kind of flatten that out, and then we're going to come back down here. Okay, let's see how we did. On Desmos, let's hide this one. It was negative x plus 1 cubed x minus 2. Wait, did I do that backwards? Negative x minus 1 cubed x plus 2. Okay, so we got kind of the shape of this root pretty good. It's flat. We got that it goes straight through here. The main thing that we didn't necessarily predict is how the function apparently is actually kind of exploding. I guess actually the function kind of goes way up here. But based on the information we had, there was no way to know that, and this sketch that we drew would have been fine. So our next topic is graphing rational functions, and this is really the main focus of the first web work assignment, or at least the first half of the first web work assignment. The second half is going to be on optimization, which we're going to cover tomorrow. So graphing rational functions, a rational function, let's just define this here. So a rational function is is a polynomial divided by a polynomial. Okay. Now, notice that, for example, 1 is a polynomial. So any polynomial is a polynomial divided by 1. And so any polynomial is a rational function. But rational functions are a much broader class of functions. So, for example, we could say like x cubed plus 2x minus 1 over x squared plus 4 is a rational function. Another example, right, 1 over x is a rational function. Okay, so the main difference, the main thing that can happen with rational functions that can't happen with polynomials is that you can have asymptotes. So when your denominator is 0, right, you're dividing by 0, so you're undefined. And as you approach something that's getting really small, you're going to explode, right? You're going to get really big or really small. So let's start with this statement. So asymptotes occur when the denominator is 0. In another sense, they're the roots of the denominator. The steps that we need to use to find steps to graph a rational function is going to be basically the same steps as we have had before. So find end behavior, find roots and multiplicities. Now this is the new step that's not included in finding polynomials, is find asymptotes and multiplicities. And our final step here is just like before, is find the y-intercept. And honestly, finding the y-intercept is probably the least important of these steps, but it does give us a little bit more information. Okay, let's go to Desmos because there's some more things that we need to think about in terms of end behavior when we have rational functions. What is the end behavior of 1 over x? as we approach positive infinity, we approach zero. As we approach negative infinity, we approach zero, right? We approach zero from the bottom as we approach negative infinity, and we approach zero from the top as we approach positive infinity. If we go 1 over x squared, we approach zero from the top either way. Negative 1 over x squared, we approach zero from the bottom either way. Right, and we could also look at this. Right, so this is going to be the same again with any even or odd power, and we looked at this earlier as well. But now I just wanted to bring this back up just to kind of focus on what's going on with the end behavior. And now what if I put an x up here? So this is essentially the same as, and in fact is exactly the same as a negative 1 over x to the 4, right? So it's going to have the same end behavior as negative 1 over x to the 4. What if I added something to this? So it's negative x plus 5 now over x to the 5th. And it's quite hard to see on this graph, but you see that when I move along here, the y value is negative. So it actually crosses the axis here, and then it comes back up. Let's see if I can multiply this by something huge so you can actually see what I'm talking about. Yeah, so you see how it swoops below and then approaches it from the bottom. So it actually is doing the same thing as negative 1 over x to the 4. And my point with this is that just like with the polynomials, how we only care about the first term, here we once again only care about the first terms. So let's say I have x squared plus 8x minus, let's go minus 7 up here, over, I don't know, x cubed minus 2x or something. Let's get rid of these other graphs. Then I'm just going to look at these very first terms, and I'm going to say, well, that's basically the same as x squared over x cubed, which is the same as 1 over x. Which means that, well, let's look at 1 over x, right, which means that we approach 0 from the top off to the right, and we approach 0 from the bottom off to the left. And once again, it is a little bit hard to see what's going on here, but as we go this way, we do stay positive, and as we go this way, we do cross back down below, and then we approach 0 from the bottom, just like we have with 1 over x. So these are our end behaviors. And let's go back to OneNote and let's add these to our end behavior list. The end behaviors that we have before are going to be the same, but these are end behaviors for things that have x in the bottom, or x to the n. So, okay, we once again have 4 options. So it's either 1 over x to the odd power, and here I'm going to kind of draw it like this. So that's the direction that we're approaching 0 from. So it's from the top or the bottom. And if we have negative 1 over x to the odd, we're approaching 0 from the bottom here or from the top here. Oh gosh, 1 over x to the even. It's going to look like this. And negative 1 over x to the even is going to look like this. Okay, so let's do a couple of examples. I'm gonna factor them for us. just to make this easier. So let's go x minus 1 squared x plus 2 over x minus 2 squared. So let's think about what we have here. So this is going to be no, I don't want to put an equal sign here, but on the top it's going to be x cubed plus something over x squared plus something. So asymptotically, right, we know that x cubed over x squared equals x. So it's going to have the same end behavior as the function x. So in this case, we don't have to use our new chart. Right? We're going to use that in our next example. Okay, so end behavior looks like x, which is this. Our roots, we have a root at, we're going to set x minus 1 to 0. So that gives us x equals 1 being a root here. X plus 2 set to 0 gives us x equals negative 2. And x minus 2, right? So if the denominator is 0, that means we have an asymptote, right? And so I'll just write this specifically because we didn't do it before. Asymptote, so x minus 2 equals 0. So x equals 2 is an asymptote of multiplicity 2. Right, and so what that means is that it looks like 1 over x squared. And if we remember 1 over x squared, and what we mean by looks like, right, is that it's the same on both sides, right? Whereas 1 over x, it's different on both sides. And so that's essentially the defining factor of, that's what the multiplicity defines. So x equals 2, we're going to draw kind of a dotted line here. And okay, and then let's do the y-intercept. So y-intercept is going to give me negative 1 squared times 2 over negative 2 squared. Sorry, this is a little slanted. So that's going to give me 2 over 4. So that's 1/2. Okay. So y-intercept is here. And okay, so starting here, we know that this minus 2 is a linear root, has multiplicity 1. So we're going to go just kind of straight up through there. We're going to go find our y-intercept. Touching this root, we know that that is x minus 1 squared. So that looks like a parabola. And then this is our asymptote. So we're just going to approach it, and we're never going to touch it. I'm going to go up like this. And this asymptote has multiplicity 2. So on the other side, it has to do the same thing. So from this side, it has to approach it as well. And then ultimately, we have no more roots. So we have to just connect back over there to meet our end behavior. So let's see how we did. X minus 1 squared, x plus 2, x minus 2 squared. So how did we do? So we went up through here, we bounced on that root, we went up to this asymptote, and then we have kind of the same behavior on both sides of the asymptote, approaching infinity. So I'd say we actually did quite well on this graph. I think our picture looks very similar to the actual graph. Okay, let's do another one. Let's just do this. Let's do x over, let's do x over x squared minus 1. Okay, so that equals x over, this time I didn't factor it. Sometimes they're not going to factor it. X over x plus 1, x minus 1. So the roots, what do we want to do first? Actually, let's do end behavior first. So this is x over x squared plus something. So end behavior, like x over x squared, which is 1 over x. So we know that kind of off to this side, we're going to approach 0. And off to this side, we're going to approach 0 from the bottom. Okay, so that's our end behavior. Our roots, we have a root at x equals 0 with multiplicity 1. So that's right here. We just have to remember that multiplicity for when we graph it. And let's look at the asymptotes. So asymptotes, so x plus 1 equals 0 gives us x equals -1, and x minus 1 equals 0 gives us x equals 1. So I'm going to put my first asymptote here, another asymptote here. Okay. And these both have multiplicity 1. Multiplicity 1, so that means that they approach the asymptote from different directions, just like 1 over x. Right, so this means approach from different directions, right? That's because we think about like 1 over x looks like this, and we have this asymptote on the y-axis here, but we approach it from different directions. Okay, so I always like to start with my end behavior, and then I just draw to the next feature. So here we have this asymptote. We have to go down, right? Actually, this is a good thing to point out, right? I couldn't approach this up because then I'd have to cross the x-axis, and there's no root there, so that's not allowed. Okay, we know that we approach this from different directions, so the other side has to approach it up to infinity. And now I'm going to continue that line through this root, which I know it just transversely goes through it because it's a line. And then we're going to approach this asymptote. I have to approach the other side of this asymptote from the other side, which is the positive infinity side. And so it's going to look like this. Okay, so I kind of got this graph that's like split into 3 parts. Looks like this. So that's x. Let's see what it looks like. X over x squared minus 1. Oops. Like this, right? Which is basically what we just drew. Okay. And let's do one more. Yeah, let's just do one more. That should be good. Let's do something kind of related because I just want to compare what these two functions look like. Let's go 1 over x squared minus 1. So this is 1 over x minus 1, x plus 1. This is supposed to be squared. Right? I guess this is kind of a review of factoring difference of perfect squares. Okay, so end behavior is like 1 over x squared. So that is going to look like this. Okay, well, you get the idea. Okay, we're saying like this. So that's the end behavior. Roots. What makes the numerator 0? Nothing, right? Numerator is always 1. Not note, none. Roots, none. Asymptotes. I should asymptote. How do we spell that? Okay. Are so x minus 1 equals 0, so that gives us x equals 1, and x plus 1 equals 0, x equals -1. Okay. Let's not draw this as sideways as that. Okay, so these have multiplicity 1, so that means that we approach from different directions. Okay, and then the y-intercept is 1 over -1 times 1, which is 1 over -1 is -1. Okay, so we have a y-intercept here. We have asymptotes here and here, and our end behavior is like this. So okay, so that's everything we need to know. So we're gonna go up here. We're gonna approach positive infinity here. We know that it does different things, so we have to come -infinity here, go through that y-intercept, come back down, right? We can't go up because then we'd cross. And then we're going to come other side of this asymptote up here and meet our end behavior there. Okay. And let's have a quick look on Desmos. What this one's going to look like, basically, we're just changing that numerator to a 1. And there we have it.
looks essentially like what we just drew here.
Okay, I think this is probably a good place to stop. Um, in tomorrow's Lecture 1B, we're going to continue our review by doing a couple more examples of rational functions. Then we're going to talk about partial fraction decomposition. We will review derivatives, just kind of a quick crash course of derivative review. And then we're going to look at using derivatives and second derivatives to help us graph functions. All right, I'll see you then.